to Moivres theorem. So let's have a look at a complex number in mod-arg form, where we have z equals r outside of cos theta plus I sine theta. If we want to investigate what happens when we raise both sides to the power of n. And if we raise both sides to the power of n, we're going to get r to the n outside of cos theta plus I sine theta to the power of n. Now, before we look at that any further, we've already looked at when we multiply two complex numbers together, all we have to do is multiply their moduli and add their arguments together. So we're going to multiply z by itself, and that's going to give us r squared, because we multiply their moduli together, and then we add their arguments. So we're going to get cos 2 theta plus I sine 2 theta. And multiplying two complex numbers z together, it's the same thing as r outside of cos theta plus I sine theta all squared. So just from this example here, when we multiply two identical complex numbers together, it looks like when we have a complex number raised to the power of 2, it looks like all we have to do is raise the modulus to that power and multiply the argument by that power. So let's go ahead and see if we can prove that true for all values of n. And we're going to use mathematical induction to do that. And from our first example, we saw if we raise in mod-arg form to the power of n, it's very obvious that r gets raised to the power of n just using simple index laws. So we're just going to focus on this part here to the power of n. So we want to know, does cos theta plus I sine theta all to the n, does it equal cos of n theta plus I sine n theta? We want to know if that's true, because if that's true, it'll work for every value of n, and this is for values of n greater than or equal to 1. So if we're going to do it with mathematical induction, we need to prove that it's true for n equals 1 first. So we'll get cos theta plus I sine theta all to the 1. Does it equal cos of 1 times theta is just theta, and I sine of 1 theta is just theta, and these do equal each other, so it's true for n equals 1. So let's assume it's true for n equals k. So we're going to have cos theta plus I sine theta all to the power of k equals cos of k theta plus I sine k theta. So we're assuming it's true for n equals k. Now we have to prove that it's true for n equals k plus 1. So let's sub in k plus 1 for n. So we're going to get cos theta plus I times sine theta to the k plus 1. Does that equal cos of k plus 1 times theta plus I sine k plus 1 times theta? So let's just tidy this up a little bit. We can say Let's tidy up. Let's rewrite this as cos theta plus I sine theta to the k plus 1 equals cos of, let's expand this bracket out, so we're going to get k theta plus I of sine k theta plus theta. Let's take our left-hand side and rewrite it as cos theta plus I sine theta to the k times cos theta plus I sine theta. So just using reverse index laws. Then, so this is our left-hand side. Now we know that cos theta plus I sine theta all to the k is over here because we assumed it to be true and it equals this. So let's go ahead and sub that in. So this is going to give us cos k theta plus I sine k theta all multiplied by cos theta plus I sine theta. Let's expand it out. So we're going to get cos k theta cos theta plus I cos k theta sine theta plus I cos theta sine of k theta. I times I is going to be minus 1, so we're going to get minus sine k theta sine theta. Let's group our real parts and imaginary parts together. So then our real parts is cos of k theta cos theta minus sine k theta sine theta. And that is just our compound angle result for cos of k theta plus theta. Let's factorize out the I of the remaining two terms. And then we're going to get cos k theta sine theta plus cos theta sine k theta. And that's just our compound angle result for sine of k theta plus theta. And that equals the right-hand side. That means if it's true for k, it's true for k plus 1. And we proved that it's true for n equals 1, so it has to be true for 2, 3, 4, and so forth. So therefore it's true by mathematical induction. And that means we have our result and the theorem holds true, this theorem up here. And we're going to look at how we can use it with some examples. Sorry, that's not the theorem. It's down here. This theorem here holds true. And we can just incorporate R into it as well. But we're going to look at how we can use that in a second. So let's write the theorem. So if we have z to the n, it's going to equal r to the n outside of cos of n theta plus I times sine of n theta. So if we have, for example, how can we simplify cos theta plus I sine theta cubed? Well, we know if we have this all cubed, that's just going to equal cos of 3 theta plus I sine 3 theta. let's have a look at it, a bit of a harder example. So we want to go to new page. So we want to express cos 4 theta in terms of just cos theta. Now, to do this, we know that if we want to cos 4 theta, we can just write cos theta plus I sine theta all to the 4. Because if we simplify this, this is going to give us cos 4 theta plus I sine 4 theta. And this equals our cos theta plus I sine theta to the 4. Now, we want to express cos 4 theta in terms of cos theta. So let's go ahead and expand this right-hand side using binomial theorem. So let's take the right-hand side and expand it with some binomial theorem. So we're going to get 4 choose 0 of cos theta times I sine theta to the 4 plus 4 choose 1. Sorry, this cos theta should be to the 0. 4 choose 1 cos theta I sine theta to the 3, cos theta is to the 1, plus 4 choose 2 cos theta squared I sine theta squared plus 4 choose 3 cos theta cubed I sine theta to the 1 plus 4 choose 4 cos theta to the 4 and I sine theta to the 0. Now, in order to help us do this, let's have a look at, we know the definition of I is it equals the square root of minus 1. And when we square both sides, we get I squared equals minus 1. Then, if we multiply both of these by I, we get I cubed equaling minus I. And if we multiply both of these by I, we get I to the 4 equaling 1. And then the pattern repeats. And this is going to help us out. So 4 choose 0 is 1. Cos theta to the 4 is just cos to the 4 theta. And, sorry, that's cos theta to the 0, which is 1. And then we get I to the power of 4, which we know is 1. And then we just get sine power of 4 theta. Plus 4 choose 1 is 4. Then we have our cos theta term. Then we have I cubed, which is minus I. And then we have sine cubed theta. 4 choose 2 is 6. Then we have our cos squared theta. I squared is minus 1. So we get a minus 1. And then we have sine squared theta. 4 choose 3 is 4. cos cube theta times I sine theta. 4 choose 4 is 1. Cos to the 4 theta is just cos to the 4 theta, and I sine theta to the 0 is 1. So let's just tidy this up. We're going to have sine of the 4 theta minus 4i cos theta sine cube theta minus 6 cos squared theta sine squared theta plus 4i cos cube theta sine theta plus cos to the 4 theta. So this is our right hand side, and let's equate it to our left hand side. So if all of this equals cos 4 theta plus I sine of 4 theta. And what we can do is we can equate the real parts with the real parts and the imaginary parts with the imaginary parts. So we need to see which parts are real. So that's all the things without the I. So that's this, and this, and they should, all of those added together will equal this real part over here. So now we can say that cos 4 theta will equal sine of the 4 theta minus 6 cos squared sine squared theta plus cos to the 4 theta. So we're close because we need to express cos to the 4 theta just in terms of cos theta, but we've got a couple of sine thetas in there. So what we can do is, let's first of all express sine of the 4 theta as sine squared theta, all squared. And we can change our sine theta over here into 1 minus cos squared theta plus cos to the 4 theta. Let's change this sine squared theta into 1 minus cos squared theta. So that's all squared. Let's expand this one out. So the minus 6 cos squared times 1 is minus 6 cos squared theta. Minus 6 cos squared theta times minus cos theta is plus 6 cos to the 4 theta. And we have our plus cos to the 4 theta. Let's keep going. We've got all this term, this binomial squared, so let's expand it out. So we get 1 minus 2 cos squared theta plus cos to the 4 theta minus 6 cos squared theta plus 6 cos to the 4 theta plus cos to the 4 theta. So let's collect like terms. So we've just got that one constant. All our cos squared, so we've got minus 2 cos squared minus 6 cos squared is minus 8 cos squared. Then we've got plus 1 cos to the 4 plus 6 cos to the 4 plus 1 cos to the 4 is plus 8 cos to the 4 theta. Now we've successfully expressed cos 4 theta purely in terms of cos theta. So that was the first part to the question. Next part of the question said, hence solve 8x to the power of 4 minus 8x squared plus 1 equals 0. And we just proved that cos 4 theta equals 8 cos to the 4 theta minus 8 cos squared theta plus 1. So hopefully you can see that it's a very similar equation to what we just proved. So what that means is we can just if we let x equal cos theta, we're going to get the same expression. We're going to get 8 cos to the 4 theta minus 8 cos squared theta plus 1. And we know we can express that all as cos to the 4 theta. And this is the equation we just want to solve. So let's go ahead and solve this. So if we solve this, we can just take the inverse cos of both sides. So we have 4 theta equaling, so cos equals 0 when we have pi on 2, 3 pi on 2. Let's go around one more time. So we'll add 2 pi to both of these answers. So we're going to get 5 pi on 2 and 7 pi on 2. So the reason we picked 4 answers was because we have an equation with a power of 4. Now divide everything by 4. So we get theta equals pi over 8. 3 pi over 8. 5 pi over 8. And 7 pi over 8. But we're not interested in solving for theta. We need to solve for x. So if we take the cos of everything, we'll have cos theta equals cos of pi over 8, cos 3 pi over 8, cos 5 pi over 8, and the cos of 7 pi over 8. And cos theta we let equal x, so that means x equals all those, and these are our 4 answers for x, and they're our solutions to the equation. All right, next part of the question. We're supposed to show that cos pi over 8 plus cos 3 pi over 8 plus cos 5 pi over 8 plus cos 7 pi over 8 all equals 0. Now, since all of these are the solutions to this equation, we can use our knowledge of the addition of roots to show this. So, because all we're doing is adding the 4 roots of this equation together, and hopefully know if we have a quartic equation, when we add all 4 roots, so if the roots are alpha plus beta plus gamma plus theta, the addition of the roots will just be minus b over a. So let's just write out the full equation that we have. So we have 8x to the 4 plus 0x cubed minus 8x squared plus 0x plus 1. And doing minus b over a, we get that all the roots must equal minus 0 over 8, which is 0. And we've successfully shown if we add the roots together, it does equal 0. Next question is we need to show that cos pi over 8 times cos 3 pi over 8 times cos 5 pi over 8 times cos 7 pi over 8 equals an eighth. Now this is just the multiplication of the roots. and we get alpha, beta, gamma, and theta if they're the roots. And in a quartic equation, the product of all the roots just equals E over A. And in this case, we get E as 1 and A as 8, and successfully shown that the multiplication of all of those roots is 1/8.